Hello everyone. We want to continue on chapter 6, and we discussed these two laws of thermodynamics previously. Now we want to introduce a new concept, which is Carnot Cycle, and that's an idealized system that we will discuss it in next few slides. But before that, we need to introduce you to the reversible and irreversible processes. Probably from the name you already know what is a reversible process and irreversible process. A reversible process is a process that doesn't leave any trace on the surroundings. For example, a frictionless pendulum that goes back and forth, it's a reversible process. It's happening continuously, and if the same pendulum have friction with the air, then it will eventually stop because of the friction, and it's an irreversible process, right? So why do all the processes in the nature are irreversible? So why are we interested in reversible processes? The reason is that it sets a limit for us in terms of how much efficiency can we get from different devices. For example, if a heat engine, all the processes in a heat engine are reversible processes, what would be the efficiency? However, you cannot really achieve to that efficiency, but it sets as an idealized system for us, right? And they are also easy to analyze because there are no inefficiencies happening. So what type of inefficiencies do we have? For example, friction is one of the irreversibilities. Heat transfer across a finite temperature difference, or mixing of two fluids that you cannot separate them. Electrical resistance, chemical reaction. You can see the list here, list of irreversibilities, right? So we don't have these complications in reversible system, and they are easy to analyze. Some other examples of these processes are, for example, if you put can of soda, which the temperature is 5 degrees Celsius, the room temperature is 20, the temperature goes up to 20 degrees Celsius, right? And this process is irreversible because you cannot automatically reduce the temperature of that soda, and you have to apply some work, which is a trace on the surrounding, right? The network is a trace on the surrounding. So some other examples of irreversible process are fast compression, fast expansion, and example of reversible process is, for example, a quasi-equilibrium expansion or compression, because the process is so slow and you don't have any friction happening, and this process is a reversible process. So some more definitions here for you. We have internally reversible process, which means that your system itself is within your system, there is no irreversibilities occurring. And externally reversible means that the surrounding, nothing happened to your surrounding in terms of irreversibilities. And totally reversible process is a process which is both reversible internally and reversible externally. So these are some definitions. All right, so what is a Carnot cycle? Carnot cycle basically, as I mentioned, is an idealized system, set a maximum efficiency for the heat engines or the refrigeration processes. So it operates between two temperatures, a low temperature sink, which is TL, and the high temperature source, which is TH. And based on that, we can calculate the efficiency of the Carnot cycle and find out how much would be the maximum efficiency that we can get from a heat engine or a refrigeration process. So if you this slide that you're seeing is a heat engine example of the Carnot cycle, and you can see that you have energy source, you have a gas, there's a piston cylinder, the gas is initially at a constant temperature TH. It is connected to an energy source. So I should mention that this process have two isothermal processes, isothermal expansion and isothermal compression, and two adiabatic processes. So remember what was the difference between the isothermal expansion, the difference between isothermal and adiabatic process. So in isothermal process, the temperature stays constant. In adiabatic process, there is no heat transfer between your system and surrounding, right? So that's the definitions of isothermal and adiabatic processes. All right, so two of these processes, we did the Carnot cycle, are isothermal, and two are adiabatic. So if you look at process number 1, or A, it's from state 1 to state 2. Your energy source is connected to your gas, basically within the piston cylinder device is connected to an energy source TH, and as the gas expands, gas tries or tends to reduce its temperature to TL, but since it's connected to the energy source, then the gas temperature stays constant during this process. So this is an isothermal process. This is a quasi-equilibrium process, so it's a reversible process that's happening here. And since there are no temperature difference happening, and the temperature within your gas system changes within a very small amount of temperature change, dt, then really your system is a reversible process. All right, so that's process number 1 to 2. Process number 2 to 3, you can see it here, and in this process you insulate your system, and the gas expands. Since the gas expands, the temperature drops, and since there is no heat transfer, this temperature drop happening, right? So this is a adiabatic system. Again, it's quasi-equilibrium, very slow process that it's assumed here theoretically. And so the temperature drops because there are no heat transfer between your system and surrounding. Okay, so next, process C is you remove the insulation, you put your system in contact with a low temperature sink, and you were at the state 3 right now. This piston is pushed, so there are some work applied to your system. So from here, state 1 to state 3, your gas is doing some work on the surrounding, right? There is a boundary work happening here by your gas. Now from state 3 to state 4, or coming back finally to state 1 that we will discuss it, you are doing some work on your gas. Okay, so you push this piston, and your gas is in contact with a low temperature sink, and since your gas is being pushed, and your temperature was at TL at state 3, right, because it's expanded, the temperature of the gas tend to increase. However, because it's in contact with a low energy sink, the temperature stays constant. Okay, and that's process 3 to 4. So it loses some heat to the low temperature sink, which we call it QL, and then we reach state 4, and then from state 4, which our temperature is TL, we keep compressing, but this time we insulate our system. So once we insulate the system, then it means there is no heat transfer. The temperature, since we are compressing our gas, the temperature tends to increase, and the temperature increases to TH, and that's basically what we had initially, right? So the gas at temperature TH, and with the same volume, same everything. So that's state 1. That's a cycle that's happening, right? So this is called the Carnot cycle, and if you show this process on a diagram, you'll see that in this picture you can see this. So initially you are here, pressure is high, right, and your gas is at TH initially, right? So this is a constant temperature line, TH, in a PV diagram, right? So remember that if you have basically a constant temperature process, PV is equal to nRT for a simple gas, right? So the relationship between pressure and volume is nRT multiplied by 1 over volume. So that's this type of curve that you see, a constant temperature process, right? All right, anyway, so the first process in the cycle was what? Was a constant temperature process, right? Or isothermal process, and the gas expands. So the volume increases while the pressure drops, the temperature stays constant. Correct? And then from 2 to 3 was an adiabatic process. In this adiabatic process, the temperature drops from TH to TL. This is the constant TL line. And then from state 3 to 4, you lose heat, your temperature stays constant during this process, and then finally you go back to initial state, which is state 1. This is a cycle, and remember, from the boundary work of a system was the area under the curve, so that's the W net out. Now this is not the network that I'm drawing here, this is the work that gas does during from state 1 to state 3. The gas receives some work from state 3 to 1, which is this area again, which is the color. So this red area is the work done on the gas. So the difference between the black and red area is the net work done by the gas, right? So this is a heat engine operating between TH and TL, and that's the maximum efficiency that a heat engine can have, because all the processes we assumed was reversible processes, right? So if you reverse all these processes, you get the Carnot refrigeration cycle. So you start at point 1. Instead of going here, you do the reverse, and you start from point 1, you go to point 2. That's again, remember, this is not this is an adiabatic process, right? But just in a reverse format. And then at a constant temperature, then a constant an adiabatic process, and then a constant pressure, constant temperature process, right? And then you will have this W net again, similarly calculated as the heat engine. This is now a refrigeration process, okay? And you're receiving heat from a in this state 2 to 3, you receive heat from a refrigeration space that you want to refrigerate it, and from state 4 to 1, you dump that heat to a surrounding area, a high temperature area, okay? Here you receive heat from a high temperature source, you dump it to a sink, and you do a network. Here you receive a network from a surrounding in the refrigeration cycle. Alright, so we'll do a couple of examples, and we also will talk about the efficiency of the Carnot cycle and how to calculate it in next videos.